No, biggest stack's gone. He said, yeah. This is it. Or
I don't care what anyone why does she want to go and just pay for it to get fixed? And then I'll let the football game if no sense. He said, I'll give you $20. I said, that gets me like half a screen. Continuity.
You guys need any help with anything? I'm available today after school. I'll probably be here till about 5 o'clock. So anytime you want to swing by after school, feel free. Let me know that you're going to come by though. Today we're talking about limits and continuity. We're making our way to the derivative here.
You're so stupid. Why is this happening? Why? Please don't miss anything else. That was it. That was the thing that made everything work. That was it.
Page 64. One-sided and two-sided limits.
that, she could do it. But she would just be short lining. Like that, they did that.
Can I go to the restroom? May I go to the restroom?
Sure. I think the pass should be hanging from the light switch.
After the F of X equals 11 out.
It may have fallen in.
Thanks.
Is that like the sign for limits, or is that you like trying to write limits in cursive?
No, L-I-M.
Oh, okay.
Yeah,
I really, I was like, what is this?
That's a good idea.
I was like,
Like a genius.
yeah. Anybody else want a textbook?
Make sure you just return them when you're done. We'll take them home, please.
But they're so pretty.
Yeah. I need 2 textbooks.
What is that school after you? Some of these things like you try to.
Hold on.
That's what I do best.
No, that wasn't. Oh, you said.
Okay. So let's first go with this same mathematical speak. You have a limit of f of x as x approaches some constant. If that's equal to some defined limit, capital L, then it should be true that if we approach that same constant from the right-hand side or the left-hand side, it should be the same limit, L, for this to exist. This is a basic principle that you guys probably already know, knowing that we must have limit approaching from the left, right, must match, or say that the limit as x approaches the constant is some defined value. If these don't match, then this does not exist.
Wait, where can I find the videos? Where?
To review this,
Yeah.
I hope you can learn in class, but
No,
the
that's what I
videos-
meant to review.
Okay, the videos would be the same as what I'm doing here. I'm still trying to figure that out. I'm talking with the IT department. Worst case scenario, if I can't do the videos, which I'm probably gonna find a way. I have to even use YouTube. I'm gonna try to throw these flip charts up ASAP. But I definitely, obviously, am making these videos. I want to have the videos available for you guys.
Up on what?
What do you mean up on what?
Where's it gonna be posted on?
Probably what, through Blackboard. When I do it, I'll let you guys know. I'll do whatever I could possibly do that's the best. Okay, any questions about this
So,
mathematical notation?
L is the limit of the constant. Like when you write L, you're talking like L stands for the limit of the constant they're talking about as versus C.
L is the limit of the function as
They approach
x
the constant.
approaches c.
Okay.
Some constant, yeah. Some specific constant, yeah. Just saying that they should match. I mean, this, what this look like here is like, so if this is some function, say f of x, the limit as x approaches 3 from the left-hand side is 3.5. It's the same as we approach 3.3 from the right-hand side, it's also 3.5. Therefore, you can just say the limit as x approaches 3 is 3.5, once they match.
So no matter which side it's coming from, it still ends up at that 3.5.
Yeah, therefore the limit exists, yeah.
Cool.
I'm not gonna focus on sandwich theorem. Speaking of food, it's not fair.
Yeah. I'm making a grocery list. I was grocery shopping with my the other day.
In the next section, 2.2, limits involving infinity. You can see what happens as x approaches infinity. This is especially nice to see when you have a graph.
But this is where you were saying it's really, it has no limit.
Gross.
The graph, if you come this way, or the limit,
Okay,
the limit
okay.
still
I've told
3.5,
them
but
several
it's
times that it's available online, so that's their fault. You can either ignore them or you can just let them know your teacher has told you that it's available online. Thank you, sorry about that, thank you, bye-bye. I did not mean to interrupt you, Grace, or the phone, what's up?
The infinite limits, that's when where it's like there is no limit, and we were talking about how ridiculous that is, and whatever.
Yeah, so if you're evaluating the limit,
Just trying to connect it back to what you were saying.
yep, so we have a vertical asymptote, and it goes up forever, so let's say you have,
Like, and you're like, the limit is negative infinity, but really it's just, there's.
right, that doesn't make any sense.
Yeah.
So, vertical asymptotes, say we have vertical asymptote 5, we have 5 here, and we have some function. And this is all the same function. Just make sure you can see who it is before you let them in. The limit as x approaches 5 would be infinity, therefore there is no limit. So there's no limit as we approach 5 from the left, right, or in general. Does not exist.
So would that be the only case where there isn't a limit? Because like, from what I can tell, I mean, if there's a graph like the one before, then in what case would there not be like the same limit on both sides unless you're thinking something like that?
Functions that oscillate, such as sine or cosine.
Okay.
Limit as x approaches 5 does not exist. Good question. Okay. So now what we're looking at as x approaches infinity, some behaviors. If you look at something that like at the bottom of page 73, the limit as x approaches plus or minus infinity of f of x over g of x. And they're defining f of x to be this polynomial 3x to the fourth, blah, 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 and g of x to be 3x to the fourth. This ends up being just 1. Now, if you look at that page, you can see that they break it up. They do actually do division. And you can see how every single term except the 1 would go to 0. 2 over 3x, as x approaches infinity, that goes away to 0. 1 over x squared will go to 0, right? The positive bottom gets infinitely larger, it's approaching 0, so it would just be 1.
So whenever you have a limit where x is approaching plus or minus infinity and you're dividing two functions, it always equals 1?
No. No. So this one equals 1 because the highest powers are matching and the coefficients are the same. So if you look at the top, you have 3x to the fourth minus blah, 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 all over 3x to the fourth. The highest degree is 4. So then you just look at the coefficients. You have 3 over 3, that's 1. So you just look at the coefficients. So
Okay.
let me give you different examples. So let's give an example. The limit, and yes, this is because it's limit LM. Limit as x approaches infinity of, say, x over x squared. What would this be equal to? You guys ever done this? Okay, so this should be equal to the limit good as x approaches infinity of 1 over x. You can simplify like that, that's good. And what will this be?
Wait,
So we just simplified x squared to 1 over x, that's fine. But what is this? The limit of x approaches infinity. 1 stays at 1, so the bottom is getting larger and larger and larger, so what value are we approaching? 0, right? 1 divided by a very large number, even larger number, even larger number, you're approaching 0. Remember, the limit is what value you are approaching. I try to emphasize that.
I'm sorry, how do we know that we're approaching 0?
Because you can always do this without a calculator, because I will give you some quizzing tests where I say no calculator, because you have to have a fundamental understanding of what's going on. Imagine you plug in a large number into x, let's say 1,000. What's 1,000? Let's continue.
Oh, so you're going to get smaller and smaller, 0.0000001.
Sure. Yeah, exactly. So.
Yeah. Okay, that makes sense.
Okay. Now, if you don't want to even write this, you can understand this principle here. Because this is a square and this is just a linear to the single power, this is going to infinity more quickly than this guy is. But you can also understand it like this. That's fine. Yes.
so if you have a limit to something and it's hard to understand, like in the way that it is, should you simplify it so that you can figure out what?
These should not be hard because you first look at the exponents.
Yeah.
If they match, you look at the coefficients. I'll show you another example. So we'll do some more examples. So the example where you have the limit as x approaches infinity of, say, x squared minus 3x plus 2 over 2x squared plus 1. Okay? These are actually nice when you have a polynomial or polynomial because you're going to infinity. You only care about the largest term, meaning the term of the highest degree. You can ignore everything else because as we go to infinity, this other stuff is insignificant.
Why?
Because you're going to infinity.
Why?
It becomes like negligible. It doesn't even matter.
Once you get to really huge numbers.
Once you get really, if you can punch it in, you're going to find out. Does anyone know what this would be?
Okay, yeah, that makes sense.
So we have matching degrees on the top and the bottom. So what did I say if we had matching degrees, remember?
But look at the coefficient from 1. So it's not 1. Or is it 1?
Matching degrees. The highest degree is 2. The degree of the numerator is 2, which is determined by the highest exponent.
But
So
then
it's
the
still
top
0?
has 3x. Like, does that
Don't
matter?
care about that.
But
Because
when you
we're
think
going
about
to
the
infinity.
numbers,
This is
where
the
does
same
it
exact
go
limit
from
as
0
this.
to 3x? Like, a million squared is gonna be huge.
This is the same exact value as this.
No, it's not the same exact.
It is the same exact, yeah.
How?
Because the limit is what value you are approaching. So as you're approaching infinity, now I could not do this if it were some constant. Let's be clear about this. But as we're approaching infinity, we do not care about the lower degree terms. We only care about the highest degree terms, both the top and the bottom.
Wouldn't it be point
But how is it
five then?
exactly?
Very good. This would equal to 1/2.
Oh,
Oh my god.
Okay,
I actually sort of finished.
And you guys can test it. You could plug in really, you can keep the original guy and plug in really large values in x, and larger and larger and larger, and you'll see your calculator
I get why
getting
like
to 1/2.
1/2 is just the coefficients, but why is 1/2 the limit?
Because the limit is what value you are approaching. So if you're approaching infinity, first off, you only care about the highest degree terms.
Yeah, I understand that,
Okay,
and
so
I
here.
understand that 1/2 is the coefficients of the x squared. Like it's 1x/2, like I.
Well, x squared over x squared is just 1/1. So
Yeah,
it's
but
basically the same
so
question
it's
as
1/2.
the limit
Yeah,
is the limit is
That's, I get how that's that, but I don't understand like conceptually how that's the limit.
because if you were to graph this guy,
Uh-huh,
it would be a horizontal line at y equals 1/2.
okay.
Where there would be a hole at 0, but it would be removable. It wouldn't be a vertical asymptote. It would just be a hole, but it would look just like y equals 1/2.
Okay.
And this is great. Like when you guys are doing work like this, you can have Desmos.com up. You can punch it in to see it. Because I'm the same way. I want to know. I want to understand why does it look. What does it look like? You would see this looks just like y
It's
equals
true
1/2.
whenever you have the exponents and all that to infinity, you can pretty much just take the coefficients and that's your limit, like every time.
Yep. When they're matching degrees, you just look at the coefficients. Exactly. That's simple.
Is the limit.
The ratio of the coefficients, yeah, 1/2, 1/2, yep. It is the answer. It's the value of the limit. We're just evaluating these limits.
All right.
So let's see another example where the coefficients don't match. So if you have the limit as x approaches infinity of x squared plus 4 over 3x cubed.
Now, would you only care about the 3x cubed?
We only care about the highest degree term in each one, because we're going to infinity. I don't want you guys to get a habit of, oh, I'll just drop off stuff when you go to some constant. No, you have to leave that in there. When you go to infinity, though, we're talking about the idea of going on forever. These other smaller terms, they do not matter in the long run, which this is the long run because it's infinity. As you're going to infinity, you look at the long run here. So if you just look at the highest degrees, x squared over 3x cubed, doesn't x cubed get larger more quickly than an x squared? No matter what the coefficients are. Even if this were like 200x squared, it doesn't matter. This guy in the long run will pass this guy eventually.
Yeah.
Okay? So this is going to infinity, and this is getting larger more quickly than this is. So what is the limit?
0.
It is 0. Because this is getting larger more quickly than this guy is.
So question.
But
So if the bottom number, no matter what, if it's getting larger, so if it has like a bigger exponent than the one on top, then you can just automatically assume it's going to be 0 because it's going to get bigger faster.
It is 0, yeah.
Yeah, exactly.
Yeah.
It's going to be. Okay, so
It is 0.
that's just like a thing to just note that if the exponent on the bottom is bigger,
Yep.
then it's going to 0.
Yep. If they're both polynomial functions, yep.
Okay.
Yeah.
So in the last one that we did, it was x squared over 2x squared.
Uh-huh.
Isn't the bottom getting bigger? Because of the 2. It has 2x squared.
Yeah, but
that
it's
is
just
no
going to be
matter what.
1/2. It's going to be like a horizontal asymptote. You
Yeah,
guys remember
what you're saying,
horizontal
but it doesn't make
asymptotes?
sense.
You
Yeah.
guys clear with that? Well,
but
this
I'm
is
saying
that.
x squared and 2x squared. 2x squared is always going to get bigger faster,
Mhm.
like no matter
This
what.
will always be twice as large as this, which is why it's constantly fixed at 1/2. Here it's different.
Oh, because it's getting exponentially.
Yeah, you can think of it as like getting exponentially bigger. Sure,
Oh, I
yeah.
see. Okay.
So
Yeah.
when your limit's approaching infinity and your denominator is getting exponentially bigger, then it's 0.
Yeah, not just if it's
Then
getting
it's top,
bigger.
then
If this degree is higher, then
Yeah.
yeah, it's going to 0.
Okay, cool.
okay.
It can also be simplified as just 1 over 3x.
Yep. Yeah, because if it's 1 over 3x, yeah, but you also see 0, yeah.
What if the top has the higher exponent?
Okay, good question. So I'll do the next example. What do you think would happen there?
Is it just
The
approaching
limit
infinity?
it would be. You're right. Exponential infinity of, say, x cubed over x squared plus 4. The numerator degree is higher, so the limit doesn't exist. Because it's going to infinity.
So if your limit is infinity, the limit is not exist.
Right.
Yeah.
Alright.
I'm not concerned about all these in behavior model definition. I really want you guys to get this. This is, I feel, the most important. Section 2.3, continuity.
A bit molly up.
Definition of continuity at a point on page 79. You have the interior point, say a function y equals f of x is continuous at an interior point c of its domain if the limit as x approaches c of f of x is equal to f of c, and an endpoint, a function y equals f of x is continuous at the left endpoint a or is continuous at a right endpoint b of its domain if this is satisfied. Limit as x approaches a from the right is equal to f of a, or approaching b from the left is equal to f of b.
Sounds very complicated.
It sounds very complicated, but all it is saying is like this. Notice, is this function continuous
Yes.
for the entire domain?
No, I don't.
Is this function continuous?
What is that dot?
It is not continuous because there is a hole. There's a hole, so it's not continuous. What's that? There's nothing there at that point. So let's be clear here that f of 3
Oh, that's
does not exist.
okay.
However, the limit as x approaches 3 does exist.
This would not be an interior point.
Make this clear distinction here. Yeah, you're right. There's this discontinuous, so it's not going to be continuous at a point. Because the limit as x approaches 3 of f of x equal 5 is not, doesn't match this guy. Here we're saying that f of 3 doesn't exist. So this is not going to, it's a very fancy math talk for saying something's not continuous. But if you see it graphically, it's very clear it's not continuous. There's a hole. What's that?
Of course, math has to make that complicated.
Yeah,
Wait, can you explain why the limit is 3.5?
yes. So the limit as x approaches 3 of this function f of x, which I should have just made blue, so imagine these axes are black, is 3.5 because the limit is what value you are approaching.
Right.
So if I approach 3, if I read the book right to left, what value am I approaching?
3.5.
I'm approaching 3.5. Even though at 3, there is no point, but I am approaching
Why is there
3.5
no point there?
because the example I made it so there is no point.
In what scenario would there be no point?
Yeah, like, what would that
Like my
function look like
equation,
right
like
now?
if you were dividing this here, like
That's why I was
x was
confused.
3 and it wasn't
There's no
possible.
equation.
This is a good question. This is what's known as a removable discontinuity. So this is where you have like a rational function. Okay, what's non-removable look like?
Just like continuous.
Non-removable discontinuity is a vertical asymptote because you couldn't remove it. So if you can remove it, you get a hole.
What does that mean though? Like, what do you mean remove it?
I'll show you.
Since when can you do
I'll
that?
show you. Good question.
Math wasn't done good.
Good question. So let's say you have, yes. Sure. The hall pass is on the ledge. So f of x is equal to, I'm going to leave it in factored form, so my life is easy. So I have, say this is good. So let's say you're given a rational function, and you get to the point where if it's not given factored, let's say you factored, you get to this point here. Notice it is true that x cannot equal 3. Just like in this example, x cannot equal 3.
So that's the point where that is like that.
But this is a removable discontinuity.
Okay,
So it's removable. So this is equivalent. It'll look just like f of x equals x plus 1, where x cannot equal 3. So this guy, before I simplify, will look just like this, which is a line, right? A line with a slope of 1 and a y equals to 1. But it'll have a hole at 3.
Oh my god. So that would be like the other thing, like the graph that you made with the hole. That would be that represented.
Well, this is a line, though.
Yeah, besides
Off the top of my head, I can't.
If that were the correct formula, like that.
Off the top of my head, I can't come up with something that would look like this. But the principle is important.
The principle would apply to this.
Yeah, the x minus 3 in the bottom would be removed. It's removable.
If it's not removable.
Vertical asymptote.
What says that's just when it's not that.
So that's when it's approaching, like, you would approach.
I got it.
You can't have a vertical asymptote, right?
Sorry, what was the question?
So,
Sorry.
when it's, what were you saying though? I was asking, so you can't have a vertical asymptote with a hole.
Because if he said it's not removable,
Yeah.
he said if it's not removable, then it's a vertical asymptote.
So that would be where x cannot be 3, so it's going to constantly approach 3, but never actually.
Right.
Okay.
I guess. Is that, you can't have a vertical asymptote with a hole? Is that
I
possible?
mean, at the same point.
Yeah. Or at the same.
No,
I'll
like
just say
anywhere.
graph.
Oh yeah, you
On
can
an
have
graph,
this
it's a
again.
vertical asymptote.
Oh yeah. So here's another example. And I'm just gonna go with the flow, I guess, probably for a while, because you guys are asking good questions, which is good. So let's go f of x is equal to x minus 3, x plus 2, x plus 1 over x minus 3, x plus 5. Now, of course, it may not be conveniently given to you like this, but let's say you factor down, or maybe it is given to you like this. You go, yay, I like this because it's factored. Okay?
There's a hole at 3.
There's a hole at 3.
There's also a hole at -5.
Hole on x equals 3, and there is a vertical asymptote
It doesn't cancel out, but it just can never hit 5.
at x equals -5.
Why is the difference?
Because this is removable.
Oh, true.
This is not removable. When you get down to linear factors, that's as far as you can go. So you would know for sure that this is true. That there's a hole at x equals 3 and a vertical asymptote at x equals -5. So this before I simplify, this function will look just like this. It'll look just like that.
But since x plus 5 is
Except there will be a hole at x equals 3. Because if you graph this in your graphing calculator, it's going to show the vertical asymptote. But you'd have to go over to at 3 to clearly see that there's a hole. Because a point is, infinitely small.
Can you show us on that website?
Yeah, so if you have Desmos, let's go ahead and do that.
Well, would you have to put in while you're graphing, would you have to put in x minus 3 on top of the other and just count on it to automatically cancel out? Because otherwise, wouldn't it not with the hole? Yeah, how would it know if there's a hole if you don't put the x minus 3?
Yeah, that's true.
Either it's going, if you're completely factored, in the top and the bottom, either it simplifies and is a hole, or if it doesn't simplify away, it's going to be an asymptote.
So
I don't know if that answers the question.
Like but when you're plugging
If
this in,
it simplifies and you cancel out x minus 3, right? It cancels out.
you would need to specify that, hold on. You would need to specify that if you simplified this function to read f of x equals x plus 2 times x plus 1 over x plus 5, comma, x does not equal 3. You have to specify that. Yeah. So let me show you what's going on here.
There's probably a not equal sign.
I'm sure there is, because graphic calculator is so magical, but I just don't know what that means.
Okay, so.
Okay, notice there's a vertical asymptote
Right there.
at equals -5. I'll even graph you the vertical asymptote, which is great. That's something you cannot do on your calculator, but you can do on Desmos. You can graph vertical lines. See that? There's a vertical asymptote. Now, if I trace this, there should be a hole at 3. So let's watch what happens when I trace this. At 3, it is undefined. So you're not gonna see it if I don't point it out, because a point is infinitely small. I can keep zooming in forever. You're still not gonna see it because the way this is programmed. Yeah, unless I trace over it, then you can see the hole for Desmos. Yes. So I want you to see that this is the exact same graph as if I wrote it like this. Except this guy is not going to have an issue with 3, but they will look exactly the same. So hold on, just 1 second. Let me do this. Hold on. One question at a time. Hold on. I just want to demonstrate this one last thing. Hold on. Hold on to that question. Okay. So here we go. So there's the black, there's the orange. Sorry, there's the black and there's the blue. I'll turn off the orange. Blue, black. They are the exact same looking function. The only difference is the black is going to have no issue at 3.
Mr. Gross?
Yes.
Did you say that was blue?
There's the blue and then there's the black.
Are you colorblind?
I don't know. I don't know. Okay.
No, I'm not. I'm just, that's.
Well,
Like,
there's no way you can describe to me what a color looks like.
I say yellow. I think yellow lights are orange lines.
So anyway,
yeah.
I'm not that.
But you don't know if you're colorblind or not?
I don't think I am, because I do wear contacts. I would have been told that many years ago, unless I'm going colorblind. So black, is this orange or red?
That's orange.
Okay, I thought it was orange. Green,
That's blue.
blue,
Yeah.
red, and this makes this one look purple. More purple to me.
Okay.
I see how you're saying. It's like a blue. It's
Okay, so there we go.
So how does this relate back to the lesson on limits? Like, you can approach it on both sides, and the 3 was a limit because it approaches 3 but never actually got to 3 because there's a hole.
This is actually the lesson on continuity.
On what?
Continuity.
Okay, so, it goes back to being either continuous or discontinuous.
Yep, so understand that this function, even though a limit exists at 3, it is discontinuous at 3. That's pretty much what I
So
want to get.
it's not a discontinuous function, it's discontinuous at 3.
It is a discontinuous function.
Oh, okay. Okay.
Yes.
So if we get a problem with the text or something, they're gonna ask us to factor, and that's whether it's continuous or not.
If you get a question on a test related to continuity, it's going to be like the theorem that is on 79. Just like if I could ask you this, and it should make sense to you, that all this is saying is that if the limit as x approaches some constant c from the right-hand side, that's L, capital L, and the limit as x approaches c from the left-hand side, the same constant, if that's also L, then the limit as x approaches c period of that function is L. Okay. Well then I may also ask you a question that is like the definition on 79, which is just saying that if the limit as you approach c from the left and the right is the same as f of f of c, then it's continuous.
Wait, what? Is that the same?
So to go along with the definition on 79, the limit as x approaches 3 of f of x is 3.5. It does not match f of 3, so this is discontinuous.
But isn't it like the limit? Hold on. It's still the limit on both sides is still 3.5.
Correct.
It's just not.
So the limit as x approaches 3 is 3.5.
Yeah.
Whether you push from the left, the right, and they match, so therefore you just say this.
Yeah.
But f of 3 does not exist because there is a hole.
So, yes, there is.
So it's discontinuous.
So that's,
So
that's all. If there was a point that's missing, then it's just.
It's discontinuous.
So that's the only answer.
So the limit, sorry, I'm like, wait,
Yeah,
I thought you were continuing.
I was, sorry. So like if, I mean, what would the question be? If there's a hole, then it would just be discontinuous, and if there isn't a hole or asymptote, then it's continuous, right? I mean, what else can you ask us that? Or unless you say where the break is. But what else would you ask for a question on that?
I might give you this piece of information and this piece of information and ask if it's continuous or discontinuous.
So it would be
Oh, that's easy
continuous
then.
if you know that there was a point at 3, if you know that f of something
It would be
does
continuous
not exist.
if f of 3 equals 3.5.
Okay.
If you know that something does not exist, doesn't that mean it's discontinuous? Because that means there's a point missing.
Yep. So that just this simple fact alone.
So
is
that would
discontinuous.
just, okay.
We would be given a function in something like this, right?
But for example, if I said
But you can't even really see them.
Well, scan through.
if I say f of 3 is 1, which it is, this is still discontinuous because it's not matching. The limit as x approaches 3 is not the same as f of 3.
It has to be on that line.
F of 3 isn't 1 though.
F of 3 is 1.
No, it's not.
Yes, it is. F of 3 is definitely 1. I plotted the
That's
point.
not
I made
on
it
F
up.
of X though.
So it doesn't count, so it's not continuous. But
F
then,
of, if it's F, it's not in the function, you just put a point there.
no, but
No, this is definitely part of the function
How?
because I made it up. I'm saying f of 3.
the line.
How did you figure
Right,
out?
that's why it's discontinuous.
How did you figure out it was 1? There's no equation.
What do you mean there's no? I just made it up.
Like what made up?
You can make a piece. You can make
So
a
f of
piecewise
3 can
function.
be anything?
apparently.
What do you mean f of 3 could be anything?
You
What
just
I have right
decided that
now.
it's 1.
Yes, this is a
So I
different.
could
This is
just
different.
decide
This
that
is a
it's
different
100, right?
different problem. I saved time instead of writing out the whole thing again. I just erased that. I plotted a point and said, I'm actually giving a value for at x equals 3. I'm saying it's 1. This one is also discontinuous because they don't match.
I don't know. There's a graph on there.
Okay,
Yeah, I see it.
So if it's not on the line, then the function is just.
There's a lot of,
There's still a
there's
point
like
here.
a ton of conversation about a lot.
How do you
You
know
kind
what
of
the point is?
let someone talk and then let someone else talk. Raise your hand if you have a question. Yes.
So I understand that, okay, like Jessica said, there's still a point where there is no point, like for f of 3, there's still a point, but it's not 3.5, like that's not,
Which makes it discontinuous.
that's a hole, so it's discontinuous, but there's still a point. How do you know where the point is?
You solve.
Because
You
it's
just
right,
decide,
it's
you
right
just
there.
decide where it is?
And you see that it's not at the
If
limit.
if you're given this, that's a point because it's filled in. A hole is a hole because it's not filled in. So
Okay,
it's-
but if you don't give it to me, how do I know where it is?
if I don't give, what do you mean if I don't give
If
it
you
to
don't
you?
tell me it's at 1, you just say there's a hole there, where is the point for f of 3? You have to solve.
Sometimes there may be no point. Like in the previous
It
example,
was undefined.
f of 3 did not exist.
Yeah, I thought it always didn't exist because there's a hole right there where 3 is on the function.
Not in this example. In this example, f of 3 is 1.
How do you know when there's a point like that or when it's undefined in the other
I
one?
don't think it
When-
matters.
Could you give us like a real example?
Okay.
Like,
All right.
just
I'll give you your
like
example.
Like where
Close
we
your eyes.
solve.
Close your eyes. Close your eyes. Open your eyes. Here's your example.
Bruh.
This is a very typical. This is a very typical problem that you would see.
I think what, like,
there's no like,
I'm pretty good.
like you just kind of like made up it's one. There's no like X's that you had to solve it. Like you just put it there. Like why?
Why do we have any examples in the math book? I don't know.
Because the rest of them
example.
make
I think we're over. I think
Let's
we're
try to
overthinking this.
understand why we put it, like, in a real problem, if we had to figure out where that point was, how would we know where it was if it was not given to us? And how would we even know if it even existed? Because in some cases, there isn't a point.
You guys, honestly, it feels like you're making it way more complicated. Yes.
Hey, what you do is just create a new function that determine it, and then plug the hole because,
You guys are trying to make things up.
When you plug 3 into the
I'm just,
equation,
if you're given this, I want you guys to understand that f of 3 definitely does exist. It is one, f of 3 is 1. There's no point here where my finger is. There's a hole.
We understand.
yeah,
Okay.
the function.
Okay, but f of 3 is 1.
Can I take a picture of it? Do you mind?
Yeah, feel free, I got to take a picture, sure. Yes.
So.
I do plan on sharing these, sorry, I do plan on sharing these flip charts. If I can't get the videos up, I'll at least get the flip charts up. Yes.
If f of 3 is 1, so there is a 3, as it's approaching 3, would you still say it's approaching, it's 3.5? Or would
It
you
is,
say it's
yep.
1?
F is 3.5.
Okay.
Good thing, good question. The limit as x approaches 3 is 3.5, even though f of 3 is 1.
If f of 3 is 1, why doesn't the line go down to 1 if f of?
What line? What are you talking
The
about?
function
Because there are no
line,
other
the one where
points
you graph the
somewhere.
function.
It just doesn't.
There are another
That's how you graph a function. You plug in a point and then you
No,
drop
this-
the point.
this is the function.
That's the point.
This is the function.
That's
There's nothing
not
wrong
how it
with
is.
just stating this. I mean, I could write it as piecewise if you want. I will show you guys piecewise next. I think you may be making it way more complicated than it is. Don't even ask why it is. The fact is they're telling you this is what it is, then this is what it is. Yeah.
So we're trying to figure out what, if we want to understand it, right? That's like,
Yeah,
yeah,
dude, you'll pay, okay.
I know how these graph lines.
Algebraically, this is like a piecewise. If you guys have questions, you can see me after school. I'm available after school. But this, if you're talking about algebraically understanding this, you can think of something like a piecewise function. So f of x is let's say it's x minus 3 for everything for except at x equals 3. But then let's say f of x is equal to 1 at x equals 3. You guys should have definitely seen this piecewise function where you say it's this for, it's this, or it's this, or it's this. Okay. So we'll go over piecewise function. Which may answer your question of what does it look like? What does it look like? Algebraically, it might look like something like this. Again, I'm available after school. Today is good day. I know it's available any other day this week, but definitely today. All right.